Welcome back, everyone. I'm very excited to present Barbara Poblete. I met Barbara at a Grace Hopper conference a few years ago, and she's a superstar in Chile. She's an associate professor at the computer science department at the University of Chile, a researcher at the Millennium Institute Foundational Research on Data, and a visiting academic at Amazon. She recently received a Google Latin America Research Award to study the effects of social media on elections. And today she's going to be talking about how hate speech detection is not as easy as it seems. Okay, I will hand it out to you, Barbara.
Hi, Andrea. Thank you for inviting me. So I hope you can see my slides. Could you confirm, Andrea?
Yes, we can see your slides.
Okay, so I'm going just to adjust my presenter setup so I can see my timer. Okay, so today I'm going to talk about hate speech in social media and Twitter, and the difficulties we have found and run into while trying to research this problem from the perspective of the Spanish language. And this, how it led us to find multiple errors in the literature, also for what was for English. So here it is. Let me see how I can move my slides. There. Okay, so this is a disclaimer. I'm not an expert in machine learning. I'm more what you would say a data mining person. So I have been doing data mining and information retrieval for a very long time, specialized in web. So I used to work at Yahoo before joining the university. But I use machine learning a lot. I also like to say this work is, I just started working as a visiting academic at Amazon, but this work is not related to anything done at Amazon, just to clarify that. My main interests are web data mining and social media analysis. I have worked on credibility analysis of rumors in social media. I do use machine learning a lot as a tool. But my focus is on the evaluation of different methods and how to select the best tool to discover knowledge. So for me, the purpose is not the tool itself, but how to select the best tool to use for a certain problem and how to validate that the results that we are obtaining are generalizable and will work in other scenarios. So the value I place is more on understanding and being able to reproduce, generalize. I value that more than gaining marginal improvements on a certain model by just tuning it. So this is how the story starts usually when we try to do things. So somebody asked me, okay, I heard you're working on problem X, in this case, hate speech detection. Also, it has been for us, we detect earthquakes using Twitter. So somebody would say, oh, I heard you're working on this, but that's a closed problem. This is already solved. So I usually get that comment. For example, when I started working on detection of earthquakes using Twitter, because we were asked to do that for Chile in the Spanish language. So while we try to adapt methods that supposedly work for English, we find a series of problems. So examples of apparently easy tasks for English are hate speech detection in social media, which reports 95% F1. Another example is worldwide earthquake detection using Twitter that reports 94% precision. And what we have found differs a lot from that. So the story from the academic perspective, this is not the same in industry, but this is from the research side, is that you find a problem, you find a labeled data set for that problem, you train and fine tune a classification model. All the better if you can use deep learning, for example, and then you report this amazing results, like the ones I have just showed shown you, and you just rinse and repeat this for every problem you're working on. And then other folks will recreate the results you have obtained for the same data set or for a different data set that is quite similar, but usually never cross data set evaluation is done. So for example, I would train on a hate speech problem with a certain Twitter data set, and then I would evaluate on that same data set. I would not try to evaluate it with different types of data. This is not the right way to do things, but this is what I have observed that happens a lot in research. So when we reviewed the literature for hate speech detection, we found that everybody was using the same data set, and they were never testing on other types of data sets, not even similar ones. So they actually reach this really good performance on one data set, and they say the problem is solved. I don't need to work on this anymore because my F1 is like 97%, so it's solved. But actually in practice, the problem is not solved, because you can see that, for example, hate speech detection, if you ask people working at Facebook or Twitter, it's one of the most difficult problems that research groups are working on, because it's not easy to detect. So how can we say that this problem has been solved when it really hasn't? Why is there this difference? Okay, for us, what we have found to be true is that you can't really say that you have solved the problem until you apply your solution or method to a different scenario. This leads me to talk about a paper that we wrote that we presented in 2019 at SIGIR, which is like one of the most important conferences on information retrieval. So the title of this paper is Hate Speech Detection is Not as Easy as You May Think, a closer look at model validation. So I'm going to go a little bit in depth in that problem. So hate speech detection has become something very important in the past years, because it's considered as part of our freedom of speech. Being allowed to express ourselves. Also, political campaigns are conducted in social media. So if you have, for example, a gender gap between how much hate women receive when they're trying to run their political campaigns on social media and how much hate men receive, or women of color receive, then you have a problem if women can't express themselves on social media. So there was actually a study that came out a couple of years ago from Amnesty International, where they actually did this research of following conversations on social media of women politicians and male politicians. And they found that women received a lot more hate speech and were very harassed in social media. And women of color were like 3 times more likely to receive hate speech, or would receive actually a very larger volume of hate speech in social media. So platforms have really tried to regulate this and try to improve the environment on social networks. So the motivation for our work was we wanted to understand why there was a gap between what scientists were reporting in their hate speech research, like this is a solved problem, versus what was happening in the real world, in the industry. Yeah, because we had examples that hate speech detection, like automatic, was not working. And the other motivation we had was that what we really wanted to do was to take the models that supposedly worked for English and to transfer this, use transfer learning to use it to detect hate speech in Spanish. There are not many resources machine learning resources for Spanish. So we have been working for some years on transfer learning to try to use languages that have more labeled data to train for other languages with less resources. And we wanted to see if there were like patterns to hate speech detection that were maybe independent of language. So if I can detect those patterns, then I would be able to detect hate speech in any language, or even detect new kinds of hate speech that my classifier hasn't seen before. So those were our research motivations to get into this problem. And as I told you, we're studying the difference between the science, like what was reported in papers, and detection of hate speech in industry. So an example of that hate speech detection doesn't really work for platforms such as Twitter and Facebook is, so here's one. There is a public apology from Jack at Twitter, and they're saying that they're really committed to increase like the collective health, openness, and civility of public conversations. And this happened because there were reports, some people reported an account, a Twitter account that was harassing other people, and they were, this was related to, I think, politics. So they had, this person had threatened, I think, somebody from, that worked with Hillary Clinton and somebody that worked with the Obamas, and told them that they would send a mail bomb to where they worked. And this all through Twitter. So these people reported that account. And this is clearly against the terms of service. Like, you cannot say that you're going to harm someone else. But this was reviewed automatically, and it was not considered to be a harm. But this person actually ended up sending mail bombs. And this could have been stopped if there had been a flag raised that would have said, this is actual hate speech, and this person is saying that they're going to harm somebody else. If we could do that automatically in a good way, then we would detect this kind of issues that could come have as a result harm to other people. So what my student Aimee did, she's my PhD student, Aimee Arango, she reviewed the literature, and she found like the most recent works at that point when we were researching this problem. And what were the metrics they reported for hate speech detection? So there was like 92% of one paper, 94%, 93%, 95%. So this is indicating to us that the problem is kind of solved. So we looked, what we wanted to do was take one of these models that was performing well in English, like 93% F1, and we wanted to reproduce what they were doing. So usually the work is like this. You have a data set. In this case, was in a hobby data set that everybody was using, that was labeled with hate speech, different types of hate speech. And you have one phase, the first phase, which is for feature extraction. And then you have the second phase, which is for the classification method. So most works are divided like that. And there was another model. The second model that we looked at was kind of similar. They used the same data set, but what they did was oversample the data, and then they did feature extraction and the classification method. So what we tried to do was to reproduce these models and reproduce this work to use it for Spanish. So our baseline approaches, our baselines were this model 1 that I described and the model 2 that I described, using a Spanish data set for hate speech. And what we did was just simply translate the tweets to English and then classify them using these two models. That was like our initial baseline. And then as our approach, what we did was that we modeled the tweets that we wanted to classify using a multilingual embedding called Muse. And then we recreated the models M1 and M2 using this multilingual embeddings for classification. So those were the methods we were comparing. The performance that we obtained was close to 50% F1. So we were really below what we were expecting. We wanted to be close to the results that were being reported in English. We use even language agnostic features, like, for example, from Twitter. like number of retweets and likes and things like that. And we reached also 50% F1. So it was like we were transferring absolutely no knowledge by using our multilingual embedding and no knowledge by translating our tweets and classifying them with the English classifier. So why were we reaching like 50% F1? Why were we so below what the 93% that we wanted to reach? So what we did was actually go back and reproduce the results of the papers for the English language. So we went back to take a look at the model 1 in close detail. So Aimee, what she did is that she actually dove into the code and we looked at everything that had been done for these papers. So the good thing was that code was available to us. So we look at this model 1 that was published at WWW, which is a very good conference in web technologies. They were using the dataset by Wasim and Hobby. They had the phase 1 for feature extraction, phase 2 for classification method, and reported 93% F1. So now I will show you this model more in detail. So we have the data set. I don't know if you can see my mouse. I'm not sure, but okay. So we have the, let me see. We have the data set. And then what is done is that they have, there is a pre-trained embedding that is tuned using the data set, the complete data set. And then from here, we extract a specific embedding for the hate speech problem. And this specific embedding is then used as the feature space for, and also tweet representation for when we do the training of the classification model. So this first phase that uses a long short-term memory artificial neural network, this phase is only used to extract the feature space. Okay, so they use the entire data set to extract the feature space using this architecture. In this case, the feature space would be the embeddings for the representation of the text. And once we have the representation, this is taken, the embeddings, and it's taken to phase 2, where we use these embeddings for our classification. So then we train with a portion of the data set and we test with another portion, and we were able to reproduce the results from the state of the art. We got this 93% F1. So it looks good. It looks like it works, okay? But actually, what happens is that this model, what it's really doing is that it's creating the embeddings to represent the data from the complete data set. So they are actually using the entire data set to create the feature space in the representation. This is not realistic. Like if you're creating a classification model, you do not have access to the unseen data. You have to take out the portion of the data that you're going to test in before you train your embeddings, because otherwise you know all the information, you're overfitting. So this is what was happening in this model. They were using the entire data set to extract the embeddings, and then they were using those embeddings that were built from the complete data set to train a model with a portion of the data set and then to evaluate with another portion of the data set. So there's overfitting by using the entire data set to create the embeddings. So actually, if we split this in train and test, and we use the train, we corrected this problem. We used only the train data to create the embeddings, and then we take those embeddings for the classification. We find that the F1 decreases from 93% to 74%. So we actually found that it was overestimated, the quality of the classification by a lot. So from 93% to 74%, this decreased. And this is just data overfitting. So now we go and look at the second representative model, which is this other paper at SIGIR, which they do a similar thing. But what they did, since there's a high imbalance between like the hateful tweets, we have very few hateful tweets. Like in the real world, we have few hateful tweets in comparison to non-hate tweets. But in this data set, the imbalance was the other way around. Okay, so what they did was that they oversampled the hate speech before training and classifying to have more representation of the hateful tweets. And using this approach, they obtain 93% F1. So what they do is that they take the complete data set. And what they do is take the non-hate tweets and keep them as they are. And they oversample ×3 the hateful tweets. So you can see it here on the diagram. They repeat 3 times the hateful tweets by oversampling. And after they do the oversampling, they will split train and test. So this was not trivial to understand from the paper. We actually had to see this by looking at the code to see exactly how they had done this process. So once they do the split and train and test, then they train their embeddings and their classification model for this problem. And they obtain 93% F1. So this kind of seems okay. I guess you might have already detected, if you're familiar with like evaluation, you might have detected that there is a problem in how they are doing this. Because if they oversample before the train and test split, you have a chance that you will have the same tweets, hateful tweets, in both train and test. So this is actually overfitting because you would have the same data across train and test. You just have to learn to be able to classify correctly. So we repeated this experiment. And let me see. Okay, so this is the illustration of how in the original data set, I would have one hateful tweet, and then by oversampling, I would have the same hateful tweet 3 times there. So it's repeated, and then I would have it across train and test. And that's the example, 93% F1. But now we correct this problem to see what the real performance would be, to try to come closer to what this model's actual performance is without overfitting. So what we do is that we take the data set and we split into train and test right away. We don't oversample or do anything. After we have split into into train and test, then we oversample the hateful tweets, but only in the training data, okay? And that way we make sure that we don't have the same tweets across train and test. Okay, so that's what we're trying to avoid. We're trying to avoid that our classifier learns the data. So it's forced to evaluate on new data that it hasn't seen before, which is what should be done all the time. And then we train our model. And then we found that the performance decreases also from 93% to 74% F1. So there was an overfitting by the oversampling that was performed in the original paper. So this is the second problem we found. So we found 2 types of overfitting. One by training the embeddings in model 1 with all the data, even the test data. And the other one that we have seen for model 2, that is by training with repeated data across test and train. So actually this problem seemed like somebody who is writing papers for these conferences should not be having these problems, but it's actually when it becomes very obscure, when you're using deep learning techniques and everything, sometimes it's easy to get confused. when you don't understand the entire pipeline of what you're doing. And you're actually trying to optimize or fine-tune your model just to obtain a better result. Sometimes it's easy to fall into these mistakes. It was very hard to find these mistakes from the papers. We had to actually go and read the code, and then we found the mistakes. So this was not trivial. This was a hard reproducibility problem. The other thing that we did that nobody had done before was we did some data exploration on this data set, the Wasim and Hovey data set from 2016. That was the most popular, and all the literature was actually, all the works in the literature were actually training with this data. And what we found was that very few users were actually generating all of the hate speech. So the sexist messages, 96% of those messages were generated by one user. Racist messages, 44% were generated by only one user, like, and so on. So there were a few prolific users that were producing all of the data in this data set. We actually had only 3 users that were producing like 90% of the hate, of the hateful tweets in the Wasim and Hovey dataset. So maybe you can imagine what kind of problem this will bring, because if you train a classifier only with the tweets and you're not telling it like who the users that have generated these tweets are, you have a very likely chance that you would have tweets from that same user across train and test. So actually, if you learn how to identify that user, if your classifier learns to identify these 3 users, it will be actually obtaining like a 90% F1. So what we're really teaching our classifier is to identify users. The classifier is not really learning how to identify hateful tweets. This is why we also saw that these approaches didn't generalize well. They were learning to identify users. So when we actually created a new data set, what we did was to evaluate this. We prevented the train and test to contain tweets from the same users across data sets. And then the performance dropped significantly, almost to like 50% F1. So the classifier was really learning to identify users. So this was the third problem we found in the literature. So what we did is that we created a new data set where we limited the amount of tweets per user. And we also prevented that the same user would be split across train and test tweets from that same user. And we recreated model 1 using this new data set that we had created from the Wasim and Hovey data set. And we also took into consideration another data set that was very similar, but had been created, it was also hateful tweets, but this third data set had been created by some other people, but it was very similar to the data set that we were using for training. So actually what we're doing is that we're training the model on a certain data set without overfitting, correcting all the overfitting problems that model 1 had. And then we're using that model to classify a different, but very similar data set. So we're actually simulating better what would happen in the real world, where you would have your tweets that you would be classifying will come from a different time. Okay, so if they're coming from a different time or a different context, it will be slightly different. So we did this test, we extracted the embeddings, we trained our classifier, and then we evaluated on this slightly different data set that had been never used as part of the pipeline for training. And the performance drops to 47% F1. So this is actually what we estimate the performance of the model to be in the real world. So we have gone from 93% F1 to the actual performance of the model how it would perform on new data that it has never seen before, it will be really 47% F1. So this is a huge, huge drop in performance for model 1, which was the best in the literature at that moment. And then we did the same for the second model, and the performance dropped to 51% F1. So we did that for model 1 and model 2. So now we have actually a better estimation. We have actually a better estimation of what the real performance of the hate speech detection approaches in the scientific literature are, what they are really performing like. So it's not 93%, it's actually closer to 51%. And if you compare those results to the ones we got when we classify our data in Spanish, they're actually the same. Okay, so that explains the gap. It's not that we can not transfer knowledge, it's just that the knowledge we're transferring is very little, actually. We're not good at solving this task. Okay, so as a summary of the problems was that the complete data set was being used in the training phase without separating this for test. Oversampling was done before the training test split, and there was a data bias. 90% of the hateful messages were being generated by 3 users, so we were learning to identify users. This type of overestimation of the state of the art is very, very common. We have seen it in other problems as well. Not many works can be reproduced, and it's a very tough job to reproduce papers like this. And the classification models have become very obscure in how they work. And it's very accessible to everybody just to take any library and apply the models. And sometimes you will have problems in your data processing pipeline that you will not detect. And this will create overfitting, for example, as we detected now. So I think that the lesson I would extract from this is that you can never target a problem without looking at the data. You always have to look at the data, and you have to analyze the data and see how it performs, and then also use your model in a slightly different scenario. Very similar, but slightly different. And if it doesn't perform well, then you're not doing your task correctly. So that's what we learned. I already said this. So actually, by using a simple classification, like a classic classifier like SVM's word vector machine, and just simple feature engineering, no neural networks, for this task in English, we were able to perform 70% F1. So actually, if you use neural networks, you got 51% F1. If you use a simple classification support vector machine, you would get 70% F1, and just feature engineering. So sometimes you try to apply the most sophisticated model when actually the solution is very simple. And by doing this very sophisticated thing, you're actually falling into overfitting and all these kind of problems. So that's important. Why were we able to spot this problem? Because we were different. Our needs were different. We needed to classify tweets in Spanish. And because we needed to do this, we had to really go in depth into how it was done in English and the models that we were trying to adapt and transfer. We had to really do that very well. And that allowed us to find the problems in the original state of the art of this, and find that this problem was hard from being solved. And in the end, at the beginning, we wanted to do a paper about how we would do transfer learning from English to Spanish. But what we ended up doing was a paper about all the experimental errors that we found in the literature. And this was our SIGIR paper. One thing I'd like to mention is that although Spanish is one of the top 5 languages that is most used on the web, it is extremely difficult to find open natural language processing resources, NLP resources, like pre-trained models, training data, and benchmarks So something that our group is doing in Chile is trying to generate these resources. We have also like written like a position short paper to indicate that we think it's really important to have artificial intelligence institutes in South America, because our reality is very different, and we can't really be buying this technology, you know, from I don't know, the United States or Europe, because if we don't understand it, then we can't really adapt it to our own scenario. So we actually need to develop to be able to produce machine learning and artificial intelligence, so it adapts to our reality and it doesn't discriminate our own people. And this also comes, from here comes also the need to create resources for languages other than English. In our case, we're focused on creating resources for Spanish. So we have pre-trained neural word representations. There was a huge effort to train BERT in Spanish. So this model was called Beto. And this was done with help and funding from many institutions because it was very expensive. We have created hate speech evaluation data sets. This comes from IME's work that are more fair for evaluation. And there's also this framework, which is very interesting, that some colleagues created also from our group. It's called the WEFE, and it's a framework to evaluate bias in word embeddings. And it's very cool. So it uses several metrics to evaluate bias, and you can actually input your different word embeddings and some query terms to measure bias, and it will output a complete comparison of all of these embeddings to allow you to measure bias according to different types of metrics. So that's very, very cool. What are we currently doing in this problem? We're really working on creating hate speech specific multilingual word embeddings. We have shown in this work that we're trying to it's under review right now, that we need much less, we need very little data to outperform sophisticated models that have been trained on massive amounts of data. If we actually create this domain-specific word embeddings for hate speech, we need like very little data, and we can outperform models like Muse and other things like that. The findings that we can actually do this task across different languages indicates that there are patterns that cut across, like hate speech patterns that cut across different languages, and they can be language independent as well. Other type of work that our group has been doing is what I was telling you before, which is like earthquake monitoring and detection using Twitter. We have a system that I will show it to you. It's like this, it's called Tweetcali. And so it's like a seismograph, but it uses only tweets, and it will tell you like when it has happened, and it takes like 2 seconds after an earthquake for the information to be published on Twitter. And this system is being used by the National Seismology Agency in Chile, and they really depend on it. Also, the Navy uses the system based on tweets. And what we had to do for this system was also, we tried to adapt work that was done for English on tweet earthquake detection. And they had done a classifier, and it required label data. And what we did was create a language agnostic approach that used language agnostic features to detect earthquakes. And as a product of that, we don't need, requires very light supervision. So you don't need training data for this, and you can basically use it for any country. So we actually scaled the task for any country. We're also able to detect Mercalli. Mercalli is damage that people experience from an earthquake, and it helps estimate how much help you need to send to somewhere where an earthquake has taken place. So it helps estimate damage, and usually it's reported by experts, and we can actually estimate that by using Twitter with very good accuracy. And we have another system for news that is called Gallium. So those are the things we have been working on lately, and all based on having multilingual needs. Okay, so that's the end of my presentation. I hope I could give you a sense of what I have been doing. I know it's a lot, but I hope I have explained it in a way you could follow it.
Thank you, Barbara. This was amazing information. I think if you read the chat comments, Kelsey saying the errors in the papers are so surprising, how many other papers are making mistakes like this, and like based on your detailed explanation, we could foresee that is happening in other machine learning applications as well. Marshall also says, this is incredible stuff. I knew this topic was difficult to address with models, but it never occurred to me that the model would pick up on users and not the text itself. And that was very obvious based on the graph that you were showing with the one user being present in so many categories. And I really enjoy hearing that your group is working on developing the resources in Spanish for NLP as well. I think like that will help a lot to the community to do applications of NLP in Spanish. And everything that you have shown today has been really good. And I have heard great things of the research that the university in Chile is doing. So I'm very happy to hear all your work. Okay. Any other questions from the audience? Brian is saying, you see this a lot in organizational settings where time matters and people just set up random splits as well. So we could probably like see examples, a lot of examples of this in industry as well.
Mm-hmm.
Thank you so much for sharing all your knowledge with us today. And we have a break until the last session for today. So we will come back at 3 o'clock. Okay.
Okay,
Thank you.
Thank you. Bye-bye.
Bye.